In this video, we're going to discuss CRA models for fraction addition with unlike denominators or different denominators. Okay, so the example that we're going to look at is 1/4 plus 3/8. Okay, so we'll look at an area model and a length model. We'll start with the area model. So here we have our 1/4 as just a circular area model. This is 1 out of the 4 equal parts that would make up this whole. This is 3 out of the 8 equal parts that would make up this whole. So here we have 1/4 and 3/8. So if we want to add these, right, when we add these together, combine these, right, we see we have 4 parts. But what would we call that, right? Like what would we call these? They don't have the same name because they're not the same size. Okay, so in order to say we have this number of this unit, we have to have the exact same unit. Okay, so what we actually need to do here is try to find some parts where both these fractions can be expressed by the same size of parts. Okay, so depending on what the fractions are, we might have to change both. In this example, we will only need to change the fourth. Okay, so we can kind of envision breaking this yellow piece into 2 equally sized parts first, okay, and which they will be eighths. Okay, but so we can kind of verify that by stacking those. Okay, so we can see that if we exchange that 1/4 for 2/8, it would be the exact same area of that circle. So again, those are equivalent fractions. That's why we're able to substitute that 2/8 in for that 1/4. Okay. So the reason that we picked eighths is obviously because our other fraction had a denominator of eighths. If that didn't quite match up, right, prior to looking at least common multiples, right, we might have to play around with this a little bit until we can get both fractions represented with the same size parts. But here we already have that. So then when we do go to add those together, right, when we're adding, we're combining, right? So now I have 5 equally sized parts. So that's where my numerator comes from, right? I have 5 parts. And again, the denominator is what is the name of the part or what is the size of the parts that make up the whole. And they're each an eighth or 1/8 of that total circle. Their name is an eighth, so I have 5/8. Okay. So again, the reason we're not able to add these as is, that 1/4, right, is because then we'd have this group that contains fourths and eighths, so we won't be really sure what to call the objects in that final group since it has 2 different labels. Okay. So that's the area model example, and we'll come back to the abstract form because we'll want to write it out a little bit more. But we'll just show the length model real quick. So for this one, I'm just going to start them all in the same line since they're different colors. It's a little bit easier to see the 2 different add-ins. So again, we have 1/4. Again, that's 1/4 of the whole, which is the red. Here we have 3/8. Each of these is 1/8 of the whole. Okay, so if we're looking at this total length, right, it's not quite clear what this is, again, because we have a fourth and then 3/8. We're not quite sure exactly where this lands. So again, kind of similarly, we need to think of breaking this in half. Again, thinking of that equivalent fractions algorithm, if we were to multiply our numerator and denominator in 1/4 by 2, right, what that means is we're doubling the number of parts that we have and doubling the number of parts that would be needed to create the whole. Okay, so we can kind of think of this as, instead of 1/4, we can think of this as 2/8 because those are equivalent fractions. Now I can easily see that my total length here is 5 units, and the units are called eighths, so it's 5/8. Okay, so those are the two examples of concrete models. Again, an area model and a length model. And then show the representational models really quickly. So kind of what this would look like in the area model, right? Here's our 1/4 plus 3/8. Again, how we show that equivalent fractions algorithm in a representational model, right? You can either draw that solid line in or kind of draw some dotted lines just to keep track. But now we can see that we have 5 total parts, right? So that's our numerator. And then we might know that these are already eighths if we can kind of think back to this, but if we just want to verify, right, we can extend all these break lines just to make the entire model composed of equally sized parts. Okay, so now I can see there's 8 parts that make up the whole, so yes, each of these are called eighths, so they're 1/8 of the total that would make up a whole, so I have 5/8. Over here we have a number line. Number lines are a little unique because if we have all the tick mark labels here, right, we can actually find that total length without necessarily needing to think about an equivalent fraction. Right. So we're at this 1/4 right away. If I already have these 8th tick marks in there, I just know I need to go 1, 2, 3. So you can just make those 3 hops and you'll end up falling on 5/8. If those tick marks aren't there, then we have to break up these units, kind of similar to what we did, breaking apart in the area model. Okay. And then I want to go back to the abstract model. This is maybe a little confusing for some since we had fourths and eighths down here. So again, what we're really doing here, and this is kind of our standard algorithm for fraction addition. 1/4 plus 3/8. And again, what we did was we found a fraction that's equivalent to 1/4. Okay, and the reason, or how we did this, was we multiplied the numerator and denominator by 2. Okay, so again, that's this action, if we're thinking of 1/4, right? When we traded this 1/4 or exchanged that 1/4 for these 2/8, right, we doubled the number of parts that we had. Right, we went from 1 part to 2 parts. That's the numerator. And then instead of needing 4 parts to make up a whole circle, I would now need 8 parts to make up this full circle. So that's where that's multiplying the denominator by 2. Okay. One thing to kind of highlight too with this equivalent fractions algorithm as part of that fraction addition algorithm is when we're multiplying, what we're doing here is we're multiplying by 2 over 2. Right, so 2 over 2, or 2 divided by 2, is equal to 1. So it's this idea of multiplying by 1, right, and 1 is the multiplicative identity, which means that our original quantity will stay the same. So in the context of this area model, kind of how we're showing this idea of multiplying by 1 is we have this area of 1/4. We can break this into as many pieces as we want. And if we're multiplying by 1, can't quite get it lined up here. If we're multiplying by 1, what that means is that the area stays the same, right? Since it's the multiplicative identity, so the identity property of multiplication. Okay. So that's that equivalent fractions algorithm portion. Okay. So then what we turned this problem into was then 2/8 plus 3/8. Right, so that was seen in all of our models. We didn't have any fourths. We didn't have any yellow parts showing eventually. We only had those blue parts, which are all eighths. We had 2/8 and 3/8. And we can add our numerators. We had 5 total parts. They're all the exact same size. They all have the exact same name, and their name is eighths. So our denominator will be eighths. So again, kind of similar concrete models, the area and the length models, and then kind of similar drawings as well, but just kind of that special consideration with that number line if we have those tick marks. And then again, this will be kind of the abstract model. This is kind of the full one on the bottom here, showing us using that equivalent fractions algorithm as part of this fraction addition algorithm.